Hello everyone, my name is Mohamed, a PhD student at PSCL Lab at the School of the Chemical Engineering. So today my topic is molecular imprinting techniques and its application in the biotechnology. At the beginning we have to know what is molecular imprinting. So actually it is a technique to create a template-shaped cavities in a polymer matrices. These cavities should have the same shape of the template molecules, the same stereochemistry, the same size, and the same everything of that molecules. So it has a template-shaped cavities. We call this. Some people describe this one as like a lock and key model. So that terminology actually comes by the 1930s by the Russian scientist called Polyakov. That one was capturing various additives in the silicon matrix. A decade later, another scientist called Pauling hypothesized that a process similar to the molecular imprinting could be responsible for the selectivity of the antibody to their respective antigens, right? Then, by the beginning of the 70s of the last century, a German researcher called Wolf discovered that highly cross-linked organic polymers could be used to make a molecular imprints with high specificity. That means could play a same role of the biological receptors to biological molecules. And then recently, the molecular imprinting polymers have been used to capture everything in the life, starting from the strains to TNT. That means from the small molecules to the high molecules, even micromolecules. So in the biological systems, the molecular recognition plays an important role in the biological systems, and it could be observed between the receptor and the ligand, antigen, antibody, and even RNA ribosomes, etc. So the molecular imprinting techniques come by this one. So we have to understand what is exactly schematic of the molecular imprinting. Imagine that we have a template with that shape, so we have to find the complementary monomers that could bind with these monomers through the functional monomers, for example, from these sites. So every functional monomer of the template should interact with that monomers with specific interactions that we will describe it in details later. Then we have to make a sampling or binding between that monomers and the template. Then after binding, these monomers will interact with the templates and we can cross-link these monomers through a specific cross-linking and we can make polymerization in a specific progenic solvent. Then we could get the molecular imprinting polymer over the template. So to use that molecular imprinting polymer as a sensor for that one, we have to remove the template again to create the cavity which has the same shape of the template. In fact, we call it recognition site. To understand it more deeply, we have to look at the 3D picture. As you can see here, this is the template monomer, this is the template monomer and the complex binding together, and this is the cross-linking also with some monomer together. Then we make the polymerization process in this one over the template, and after we remove the template we can get the same shape and the same cavity that's complementary with that shape of the template exactly. So as I said, what is the imprinting methodology of that molecular imprinting technique depends on. Actually, we have three methodology of this one, which is covalent molecular imprinting, non-covalent molecular imprinting, and semi-covalent molecular imprinting. Let's start with the covalent molecular imprinting technique. From the name covalent imprinting, that means there is a covalent bond between the template and the monomer together. So Once we need to remove the template, it's more difficult because it's covalently interacted with the monomers, and that's resulting in reduction in the number of the templates that can be imprinted in this one. Actually, this method has some poor kinetics of the rebinding. In contrast, non-covalent molecular imprinting, which could be like electrostatic interaction, hydrogen bonding interaction, dipole-dipole interactions. All such kinds of interactions, we call it non-covalent interacting between the monomer and the template. Since we don't have the covalent interaction here, it's more easy to remove the template from the polymer, and that's resulting in good recovery of the valuable templates and accessible binding sites. Then we have a rapid kinetics of the rebinding again because it is non-covalent interaction. But in case of semi-covalent molecular imprinting, it is a mixture between the covalent and the non-covalent molecular imprinting. That means the interaction between the monomers and the template in the polymerization process, it is covalent interactions. But after removing the template, which is actually more difficult because it's covalently interacted with the monomer, once we could remove that one, it is the rebinding again through the non-covalent interactions, which could be like hydrogen bonding or electrostatic interaction, and as you can see in this example. So it has a rapid kinetics of rebinding, as we can see here. So the polymerization process methods, it is like normal of, it's like all the polymerization methods, which could be bulk polymerization, precipitation polymerization, suspension polymerization, and sol gel methods, surface imprinting, and in situ polymerizations. But in case of the bulk polymerization, which could be conventional MIP preparation methods, it has some limitations here in terms of deeply embedded binding sites could be created through that one, and which resulted in the slow mass transfer. And finally, it's moderate sensitivity and selectivity because there is incomplete template removal of this one. Because of the deeply embedded binding sites, we cannot completely remove the template from that one. And in case of the sol gel methods, it's actually it has slow sensitivity, slow diffusion kinetics, and long response time. So we have to find which one of these polymerization methods is could be like give a good result. In my opinion, is in situ polymerization has some advantages over the bulk polymerization and sol methods and even suspension polymerization, because in situ polymerizations, which could be like electrophotothermal in situ polymerization, in this in situ polymerization we could control the layer thickness and the layer density of the surface of the nanoparticles over this one. So we could synthesize homogeneous and controlled polymer coating films over the nanoparticles or over the substrate. As I mentioned, the applications of MIBs, it has several bioapplications. It could be used in the immunoassays. It is extensively used in the chromatography analysis, and it facts in it is like mimics of the antibody receptors. Could be used in the solid phase extractions, and also it's widely used in the catalyst and the biosensor applications. I will just choose 2 or 3 applications, which is here detection of the drugs. From the statistics, the pharmaceuticals in the wastewater is high concentration because 90% of the consumed prescription drugs ultimately end up in our wastewater. One of these drugs is the carbamazepine, which is carbamazepine. It is anti-epileptic drug, anticonvulsant drug, and could be prescribed also as a mood stabilizing drug. The high oral consumption of these drugs leads to severe effects including neurotoxicity and dizziness, and even the blurred vision or leukopenia. It is it has a strong toxicity for the ecological biota and the chronic effects in the presence of other pollutants which couldn't be excluded in fact. So now we are going to detect the carbamazepine using the molecular imprinting techniques. Now we are going to describe the proposed mechanism to detect the carbamazepine in this case. In this case, we are going to use the upconversion nanoparticles here. Upconversion nanoparticles, it is a kind of nanoparticles that can be excited by the NIR radiation to emit the visible light here. Then this is the carbamazepine, our target, and those are the monomers that could be used in this proposed mechanism. We have also AZNY here as a photoinitiator, ethylene glycol dimethyl acrylate as the crosslinker. So once the upconversion nanoparticles excited by the 980 nanometers laser, it could emit the green light here, which overlapped by the absorbance of the OZNY according to this figure. Then the OZNY excited by that emitted light then can start to induce the polymerization around that one. So we could reach to the thin layer of the MIP containing the carbamazepine in this one. After extraction process, we can find the sensor here, just has the cavity of that one. So this image could be a good description of that size. So the carbamazepine could be over that layer of that one. So after removal of the carbamazepine, we can find the cavities have the same shape, chemistry, size, even the size of the carbamazepine. Another application which is the biological recognition elements or any other biological molecules. In case of the biological recognition, which could be microorganisms, antibodies, enzymes, tissue, DNA probes, or even the cells. This biological recognition has some limitations as I described firstly, has poor stability of the biomolecule itself. It has poor reproducibility. There are some problems also associated with the sterilizations. In the biological binding, in fact, it takes a long time. So, in case of the, for example, in case of the ELISA, it requires a complex protocol and harsh environmental process. So we need to find synthetic receptors. These receptors has a promising alternative to the biological receptors for using the biosensor. These also receptors should be more stable, should be reproducible and reusable, and it would be great if it could be like portable and easy to use. So we are going to apply the molecular imprinting techniques in this field. The biomolecules that we are going to detect in this another scheme, which is alkaline phosphatase. ALP is a biomarker of the periodontitis, which could be happen in the tooth. What is the periodontitis? It is inflammation of the gingiva or in the tissue surrounding the tooth. This ALP, it is a destructive disease. Periodontitis, I'm sorry, it is a destructive disease which ultimately leads to the loss of the tooth if it's affected by that one. So early diagnosis of this disease is very important so we can save the teeth, right? So Alkaline phosphatase is one of the most important peritonitis biomarker in the saliva. So the concentration of the healthy is around 18 unit per liter, but in case of the peritonitis patient, it is over than 80 unit per liter. It is also worth to know that the high concentration of ALP is a biomarker for many diseases like for liver and the bone. So now we are going to detect that one. The proposed mechanism of this one, we need to make non-enzymatic electrochemical ALP sensor, because most of the sensor that's used of the ALP is enzymatic, so it takes long time. So we need to save the time and to need to also find out some more easy to use and another most cheaper economic sensor. That's why we are going to apply the MIP technique in this field. So we have a gold electrode here, and then this is the ALP. We have to find another polymer, which conductive polymer, in case monomer in this one, orthophenyldiamine. So we will polymerize that one over the ALP through the interactions. The main moiety of the ALP here is the cysteine, which could make a possible hydrogen bond interactions between that one and the orthophenyldiamine, as you can see here. So after polymerization, we can get the clear of the MIP, including the ALP inside it. Once we remove the ALP, this one, so there is a cavities here that can pass the current of this one. So alternatively, the current and the conductivity, we can detect the concentration of ALP, because the current will pass of this one in case of the electrochemical ALP sensor. So if we could choose this one, the alternative that signals could be calculated, and we can make the strip of this one so it could be a flexible sensor. Thank you so much for this presentation, and if you need more information, you can contact me through this email and phone number. Thank you so much.